Hydrogen. We hear a lot about it in the news. Is it the fuel of the future or more of a boondoggle or something in between? Joining me today to discuss a wide arc of the pros and cons of hydrogen is chemical engineer and process development expert Paul Martin. Paul works at Spitfire Research and has had a lot of experience across the chemical process industry working with hydrogen and syngas. Where might hydrogen fit into a lower carbon, more sustainable future? Does it have net energy, affordability, scalability aspects to it? Is it really an energy solution or more of an energy problem? This is the first of podcasts I've had with a hydrogen expert. Let's dive in on this topic with Paul Martin. Hey, Paul, good to see you.
Hi.
Thank you for taking time to be here. I saw you on a Biophysical Economic Institute webinar talking about hydrogen, and you know that topic, north, south, horizontal, vertical, net, gross, and I thought you would be a great guest to have on to update us on hydrogen reality.
Well, glad to hear that. I have a lot of people accusing me of hating hydrogen, but it would be a very strange choice of career if I hated hydrogen. I've made an awful lot of it and used a lot of it. So I don't hate hydrogen. I just really think it's a bad idea to waste it as a fuel.
Well, we're going to get into that. I don't like to categorize things as like or dislike or hate or love. We're just trying to get a biophysical map of what works, what's our reality, and what are paths forward, and maybe hydrogen can play a role. So I imagine when you were 12 or 14 years old, you were not a hydrogen expert. What managed to get you from your teenage years to your current role of energy expert? What was the path that got you here?
Well, I was very interested in photography, which got me into darkroom work, which got me into chemistry, which got me into chemical engineering. And it was in chemical engineering school at the University of Waterloo that I really got interested in climate change and, the transition that we inevitably have to make away from burning fossils as fuels. And hydrogen is a seductive, kind of simple-minded first attempt at doing that. It's what do we burn aside from fossils? Well, if we burn hydrogen, we get water. So it's the simple-minded thing to reach for that every chemistry textbook, points you in the direction of. And that's how I came to be thinking about it from an energy perspective. But I actually, when I was doing my master's degree, I was using hydrogen every day. I was working with it and contending with its terrible properties and so on as a chemical, and got to know it very well under those circumstances. That's kind of how I got to understand about it. And then I spent 3 decades working with it, making it and using it for clients, and making synthesis gas, and which is mixtures of hydrogen with carbon monoxide and so on, and trying to use it for all sorts of purposes. So I got quite familiar with it.
Excellent. So many watchers, listeners of this program probably are reasonably well versed in hydrogen, its pros and cons, but many probably don't know a lot about it. Maybe we'll just start out with a speed round, and I can ask you just some real basic questions, kind of 30-second short answers, and then we'll get into kind of an advanced take. So what is hydrogen, and what generally do we use it for in our current economies?
Sure. Right now, hydrogen is one of the largest commodity chemicals that we use. So it's a chemical, and that's all it is. It's just a chemical. It's used in a variety of different things, but the most important ones are pretty important to human thriving. So for instance, about a third of the hydrogen that we make in the world, we use to make ammonia, and ammonia is the basis of the whole nitrogen fertilizers and chemicals industry. And that literally feeds half the humans and their food animals on Earth. So it's pretty hard to imagine something more important than that. We don't use it as a fuel. We don't use it as an energy storage medium. We just use it as a chemical.
So, but ammonia comes from natural gas.
Well, ammonia comes from hydrogen, and the hydrogen comes from natural gas. And 99% of the hydrogen in the world right now, about 120 million tons of it per year, is made from fossils without carbon capture. So the notion that hydrogen's a green thing is maybe, a statement of future or wishful thinking, if you will, about what the future might be. It's certainly not a statement of the present. Hydrogen today is a fossil fuel made from fossil fuels without carbon capture.
So other than ammonia, what are a couple, 3, 4 other uses that we use hydrogen for today?
Okay, so another big use, it's a use that's very popular today, but it's going to go away in the future. About another third of hydrogen is used to desulfurize fossils before we burn them. So to get rid of sulfur from things like petroleum and natural gas, to desulfurize
and why do we need to get rid of the sulfur?
Well, because if you burn fuels with sulfur in them, they make sulfur dioxide, which turns into acid rain and is also really toxic. So we really need to get rid of that. And so we've got very strict rules about sulfur content in fossil fuels. But of course, in the future, we won't be burning fossils as fuels because we can't tolerate the CO2, much less the sulfur dioxide that comes out of them when you burn them. So we'll have to transition away from that. So right now, about 40 million tons a year of hydrogen is used to refine petroleum and desulfurize it. And in future, we'll need about 10 of that. So about 3/4 of that will go away. The other 10 we'll need because we'll keep using petroleum and gas to make chemicals and materials like plastics, and we'll still need to desulfurize those.
And any other major uses of hydrogen?
Yeah, it's used to make methanol. It's used to make a bunch of different chemicals that I won't bore the audience with, but it's also used as a coolant in electrical equipment and gas turbines and other things. By and large, it's used as a chemical for those purposes that are mentioned. Also, about 10% of it is used to reduce iron ore to iron metal by a process that's called DRI, or direct reduction of iron. But again, that's done not as pure hydrogen, but as hydrogen mixed with carbon monoxide that's made from natural gas.
And what percent of our current hydrogen now comes from fossil fuels?
99.
And the other 1% comes from?
The other 1% is a byproduct of making bleach and sodium hydroxide and chemicals like that by the chloralkali process. Actually, that's about 4% of hydrogen production, but only about a third of that is made from green electricity or nuclear electricity, and the other 2/3 is made from fossil electricity. It's not green either.
Okay, so earlier you mentioned in your darkroom and college chemistry that you learned that hydrogen has terrible properties. What did you mean by that?
Oh my goodness, yeah. It's really, when you start working with it, you learn it becomes a love-hate relationship because it does really cool things from a chemistry perspective, but from a mechanical engineering perspective, it's just really difficult to work with because it's very small. It's a very small molecule. And so it wants to go places that you don't want it to go. Like it wants to sneak out of every seal, every flange gasket, every, stem seal on a valve. It wants to leak out of containers. It wants to leak right through the grains of metals and permeate between the grains of the metals. To give you an example, this is kind of tell you how extreme this stuff is. the company I used to work for designed and built pilot plants for the chemical process industry. Those are, kind of prototype facilities that are used to test new chemical process ideas that are working in the laboratory and see how they're going to work commercially, and to get all the data that you need to do that safely and figure out if it'll make money and the like. And so one of the things that we did a lot of was hydrotreaters and hydrocrackers for petroleum. So again, those are the reactions that take out sulfur and other molecules from petroleum before you can use them as fuels or products. And so in those units, we'd use hydrogen at high pressure, and we had these devices that measured the level inside containers, inside tanks, and so on. And those devices measured the level by measuring pressure with thin diaphragms made out of stainless steel that would flex backward and forward depending on how much pressure was on them. Hydrogen would diffuse right through those diaphragms, right through the solid stainless steel, and get on the backside and start affecting the measurements. And in order to slow that down, you couldn't really stop it, but to slow it down, we would gold plate the diaphragms. That's how sneaky this stuff is. It moves right through intact metals, and that causes all kinds of problems. It can cause materials to get brittle. It can cause them to break sooner than they should. It can cause damage. And in plastic materials, it'll just walk right through it. It'll just permeate right through it and leak into the atmosphere.
There's an economic damage there, because if you bought 100 units of hydrogen to use and it's sitting there for a few months and you only have 70 units left because it escaped, that's an economic damage. But is there environmental damage if there would be a large scale use of hydrogen one day and it would be escaping from everywhere?
So there's two kinds of scary things about hydrogen leaks. The first one is, of course, it's very flammable, and it has a very wide explosive range, very low ignition energy, so it's very easy to light it off, and wide ranges of different concentrations and mixtures of hydrogen with air are capable of being ignited. So much wider range than with methane, for instance, that makes up most of natural gas. But the other thing is it's also quite a powerful greenhouse gas, and not in the simple way that CO2 is a greenhouse gas. It's a greenhouse gas by virtue of the fact that it messes with the garbage disposal in the upper atmosphere. So the upper atmosphere has a lot of intense radiation from the sun, and it makes a whole bunch of very transient chemical species called free radicals. And hydrogen quenches those free radicals and hence stops the upper atmosphere from destroying things like methane that are powerful greenhouse gases. And as a consequence, it gets assigned a global warming potential, just like methane does. And that's a multiple of that of CO2. So on the 20-year time horizon, hydrogen's about 20-year time horizon, it's about 33 times as warming as CO2. And on the 100-year time horizon, it's about 11.5 times as warming as CO2. So if you compare that against methane.
And the reason for that is because hydrogen is not a greenhouse gas itself, but it interrupts with other processes that help mitigate methane and other greenhouse gases.
Correct. It slows down the destruction of powerful greenhouse gases in the upper atmosphere, and hence adds to global warming.
Now, is the reason that very few people are concerned about that, at least in the public press, because when we burn hydrogen as a fuel, then that doesn't happen. So this risk that you're talking about in the garbage dump in the stratosphere is only if it escapes in an unburned state?
So yeah, I think part of it is that people are selling the meme of hydrogen rather than its reality. So that they're selling the truth about hydrogen that you can tell with your head nodding yes, and not the truth about hydrogen that you have to tell with your head nodding no. There's a famous Simpsons episode that gives a very excellent explanation of the difference between those two kinds of truth. Anyway, the thing about hydrogen is they'll say, well, when you burn it, you only get water. And that's true if you burn it on a catalyst, like in a fuel cell. It's not true if you burn it in a fire. Okay, so if you just light a hydrogen tube, a jet of hydrogen on fire, you're going to make nitrogen oxides the same way that you would make it if you burned anything else in air. It doesn't matter if you burn wood or petroleum or natural gas or hydrogen. If you burn it in air at high temperature, nitrogen in the air reacts with oxygen and makes nitrogen oxides, which are toxic. They cause asthma. They cause acid rain. And one of them that's not produced very much by combustion, but is produced to some degree by combustion, nitrous oxide, is not particularly toxic, but it's a very persistent greenhouse gas itself. So, but the thing is, I guess in past people thought that hydrogen had a global warming potential, but it wasn't very bad. They figured it was about 5 times that of CO2, but recent research has indicated that in fact, it's much worse than that, especially on the short time horizon. So that's kind of recent knowledge.
So if I'm going to go all over the place here because I'm actually learning along with our listeners. If we somehow were able to massively scale the hydrogen economy, as some of the memes in the news are portraying, would we have to then change some of the IPCC CO2 forecast because of some of the things you just said? Because I haven't seen that in any of the models or discussion, really.
Mm-hmm. Yep, that's absolutely true. If we were to try to replace natural gas with hydrogen, we would have to contend with hydrogen leakage rather than methane leakage. And in fact, if we make the hydrogen from methane, which, by the way, is what the fossil fuel industry wants to do, we would have to contend with both methane leakage and hydrogen leakage. So, in fact, I've put it very clearly, the problem with hydrogen as a decarbonization strategy is that hydrogen is actually a decarbonization problem. It's a decarbonization problem we have to solve. And feeding humanity and their food animals is one of the things that's on the hook for us if we don't solve that in a decarbonized future. And it's being pitched as a decarbonization solution, right? Whereas it's the decarbonization problem. So that's really worrisome.
So that leads into my follow-up question. For the things that we use hydrogen for now, you mentioned ammonia and desulfurization. Is hydrogen substitutable, or is it critically unique in its functions that it offers humanity?
Yep. There's no substitute for hydrogen in making ammonia, and there's no substitute for ammonia in growing food. So there are things we can do and should do to reduce how much ammonia that we produce to make nitrates and other things, urea and the like, for use in fertilization. It's important that we do those things because using nitrates and urea and ammonia in fertilizing crops results in making nitrous oxide in the soil. The soil organisms do it. And so there are things we have to do in order to reduce how much nitrogen fertilizer we use. So there's less runoff, there's less nitrous oxide generation, and there are fewer other problems associated with it. But there really is no substitution. I mean, in 1911, when the Haber-Bosch process for making ammonia was invented, the following years, the next couple decades after that, saw a doubling in crop yields directly as a result of just the fact that we could now fertilize fields with nitrogen. Okay. And we humans are now half the nitrogen cycle on Earth. So if you were to look at the nitrogen atoms in the proteins in your own body, half of those came from the Haber-Bosch. Okay. That's how important this stuff is. It's so critically important. And people that think we're going to switch to regenerative agriculture and just eliminate the need to make ammonia from nitrogen in the atmosphere are just kidding themselves. It's not practical.
So I'm so glad you're here, Paul, because I've stated what you just said in some papers and in the past, and I never knew who to ask this question. How do we know that half of the nitrogen in our cells comes directly from the Haber-Bosch? How could one prove that?
Well, I mean, it's in fact measurable. We understand the respiration of plants. I'm not a biologist. I'm not I own a farm. My neighbor farms the fields for me because I'm too busy earning a living here in the city. But the reality of the situation is that we know what it's like to try to farm without adding artificial nitrogen, and we know how the soil organisms fix nitrogen, and that we can do crop rotations, and we can use animal manure, and we know all of that stuff. We know all that stuff in the 1890s. We were actually really awesome at so-called regenerative agriculture in the 1890s, and crop yields were half what they are now. And as to that statistic of us, we humans being half the nitrogen cycle on Earth, again, that's something that you can calculate from a mass balance, and that comes from a professor in Western Canada named Václav Smil, who honestly I think is quite a difficult guy. Not necessarily the best influence on the whole decarbonization debate, because I think he messes up on a few things, but he does get that one right. And he's got, if you want to look up the technical reference for it, you can get it at a Smil's paper.
Well, I know Václav, and I'm trying to get him on the podcast, but he's too busy writing books.
Mm-hmm. He's too busy committing the second sin of thermodynamics as well, and that's the bone I have to pick with Dr.
I'm gonna get to that. I have that up ahead. But on this issue, it's a mass balance thing. It's how many calories are we growing from these chemical inputs. But if you took a microscope and looked at the nitrogen in my body, it wouldn't have a chemical signature from methane.
It's not like CO2 where you can look at whether the CO2 is carbon 12, carbon 13, or carbon 14 and figure out whether it's old or new. So you can't really do it that way. It's not like the nitrogens that come from Haber-Bosch are colored purple or something. But you can do a mass balance, and you can calculate, if you look at the number of calories that are generated and the yield and the nitrogen uptake required per calorie of crop, cereal crop generated. I mean, those figures are all understood. They're all knowable, and we know how much ammonia and urea and nitrate are used, because those are industrial chemicals that are taxed. So we keep record of all those things that are, produced and taxed. And as a consequence of that, we have a pretty good estimation of how much nitrogen fertilizers made and used in the world, because we don't tend to make it and then not use it.
As you're well aware, since we scheduled this interview, even the hydrogen hype in the news is accelerating. And our media portrays hydrogen as the fuel of the future, kind of in a similar way to nuclear fusion. What are the current nominal stories told about hydrogen and its future in our economies? Before you criticize them and give pros and cons, what are some of the stories that we're being told about hydrogen now?
Oh, sure. The meme of hydrogen is portrayed as the Swiss Army knife of decarbonization and energy use and storage. It's super useful for all sorts of purposes, and it's a general purpose tool. You can use it for transport. You can use it for heating. You can use it for comfort heating and industrial heating. You can use it for energy storage. You can use it for energy transport from places that are rich in energy to places that need lots of energy but are poor in the potential to generate it. So that's the story that's being told, right? And we're always told that hydrogen is the fuel of the future, and I agree with that. It really is the fuel of the future. Problem is, it's unlikely to ever be the fuel of the present.
So this is a receding horizons question. That
it's
XYZ
like nuclear fusion. It's exactly like nuclear fusion. Nuclear fusion, the way I always put it is that there are a bunch of constants in the universe. There's pi, and there's Planck's constant, and the gravitational constant, and the number of years into the future that fusion will be a practical source of electricity generation. Those are all constants.
So, well, the same thing with oil shale and massively scaling algae into biofuel. It's if oil gets to $200 a barrel, then we will be able to do this. And that statement assumes that everything else holds on.
Sorry,
all the other inputs will go up too.
When it's $200 a barrel, then they'll find out it'll take $300 a barrel. So
exactly.
Here's the crux of the matter. We've had this great party burning, millions of years worth of stored solar energy in the form of fossils every decade. And that party's gone on for 300 years, and it's resulted in an incredible thriving of humankind and, release from abject poverty and slavery for billions of people. But the party's over, right? And of course, people want the party to keep going on any way they can, and they reach for anything. And hydrogen is just one of the things they reach for, because of course you can make hydrogen from fossils and then capture and partially capture and partially bury the CO2 that comes along with it. And that's sort of better than burning fossils if you do it right. Do you know what I mean? So the trouble, of course, with all these schemes is that the devil's in the details, right? And in fact, he's not hiding in the details. He's there waving his pitchfork at you from the details. So
this is something that I've been saying for a long time. I liken the transition away from fossil fuels to the tragedy of the energy investing commons, which is eventually, and now with Ukraine, Russia situation, rather suddenly, society is realizing that energy is frickin' important. And so all of a sudden we're trying to get things that are energy for lots of reasons, but we're focusing on the output. This process gives us energy. That's good, but we're neglecting the Rube Goldberg mousetrap and all the crazy inputs that have to go into the product and the net energy losses along the way. And I think that's what you meant by the Simpsons feel good nodding your head meme, is we're just looking at the output without looking at all the inputs. What do you think about that?
So I mentioned that people are talking about hydrogen as being the Swiss Army knife of the energy transition. And, the applicability of that analogy is ironic. It's just deliciously ironic. Because if you think about a Swiss Army knife, it's kind of handy in a pinch, but it's never, if you had the right tool, you would never ever reach for your Swiss Army knife instead, right? Like it's a terrible can opener. It's not a particularly good knife. It's an absolutely miserable screwdriver. You end up slicing your finger every time you slip off the screw if you ever try to use it. So it's never the tool that you would reach for out of choice. It's kind of something that you reach for out of desperation because you're back in the woods somewhere and camping, and it's better than using a rock. And hydrogen is very much like that in terms of wasting hydrogen as a fuel, using it as a fuel. It's not something that people reach for by choice. It's something they reach for out of desperation or a lack of imagination. And, therein lies the problem. When you reach for something because you're desperate, you're not necessarily making the most informed choices. So, yeah, my problem with hydrogen is that it's neither energy efficient nor is it effective as a fuel. And that's for reasons that you can't fix with innovation. So, you can't invent a way to make hydrogen an effective or an efficient fuel.
Hold on to that. I'm gonna ask you to unpack that. But first, the final question in the introductory section here. There are a growing list of colorful descriptors of hydrogen. Could you, for the audience, just quickly run through blue, black, green, gray, pink, etc., the different types of hydrogen and what they are?
Here's the very simple answer. They are the colors of euphemism because all hydrogen requires a word that we don't have in the English language, which is something that's blacker than black. The way that we make 99% of the hydrogen in the world is we make it by reacting fossils with steam and producing the hydrogen that way and releasing the CO2 to the atmosphere. So if you take a joule of
an energy loss as well.
Yeah, if you take a joule of energy in the form of hydrogen, it's 1.4 times as emissive in CO2 emissions and methane emissions as the same joule that you would get from just burning the natural gas to begin with, unless you capture the carbon and store it. And if you make it from coal, it's even worse. It's 2 to 3 times as emissive.
So from a climate standpoint, if we didn't care about money or economic growth or net energy, just from a climate standpoint, using hydrogen for a fuel generated from fossil fuels generates 1.4 times the emission impact as burning the original fossil fuel?
If you don't capture the CO2, yes, that's accurate.
If you don't capture it.
That's correct.
And
That
how
is
much of
accurate.
that 99% of hydrogen that goes to ammonia, et cetera, is sequestered today?
Uh, a tiny fraction of a percent. A tiny
So right
fraction of a
now,
percent.
hydrogen in our world economy is actually, our use of it is a greater deleterious impact on climate than the fossil fuels used to create it.
That's right. And it's a GHG emissions sector that's bigger than aviation. Just making hydrogen right now emits more
know
CO2
that.
than the aviation industry.
How can the entire climate community not be squawking and talking about this all the time? I didn't
They're
know that.
hoping that we're going to make hydrogen from renewable electricity. It's just hope. And in fact, I've been referring to this hope that's been, using people's willing suspension of rational thought as a, their hope as a way to shut off their rational minds. I've been referring to it as the drug hopium. Now, I didn't come up with the idea of hopium, and people have been talking about hopium since the first time Obama ran for the presidency, at least, and maybe before that. But the whole idea here is that, people not thinking clearly and rationally about things let their hope run away with them. And they say, well, we could use vast quantities of electricity to make something that we can burn, and then we could use it in place of things that we burn right now. And wow, wouldn't that be a wonderful world to live in? But the devil's in the details, and he's not hiding.
I wonder if it's hope or fear, because if given a choice, we either have to use less or we could create a lot more hydrogen. People are going to choose the hydrogen route, even if it's a nodding your head sort of naive way.
Or we could do it smarter. So, the wrong solution is, the wrong way to ask the question is, we can't burn fossils anymore. What else do we burn? Right? Because the answer to that, you can hear Eric Idle from Monty Python saying more fossils in the background. It's the wrong way to think about it. We shouldn't be looking at fuel substitution. That's just simple-minded. Instead, what we should be saying is, we can't burn fossils to do this thing anymore. Move people around, keep our houses warm, etc. Whatever it is, heat something up in industry. How else do we do it without making greenhouse gas emissions? That's the question we should be asking. And the answer to that question is almost never make hydrogen from electricity. Okay. And making hydrogen from natural gas and burying the CO2, the trouble with that is, the worse a job you do of it and get away with it, the more money you make. So back to your original question, which was about the colors of hydrogen. They're all the colors of euphemism, as I mentioned. They try to make this pretty spectrum, but the reality is 99% of hydrogen is blacker than black, and we don't have a word for that. What is that? Black hole black or something? What is
black hydrogen?
You see, there's the thing. In this lexicon of colors, black hydrogen is used to refer to hydrogen that's made from coal, which is about a third of the hydrogen in the world. Okay. And then they call hydrogen that's made from natural gas, they call that gray hydrogen, even though it's 40% more emissive than just burning gas. And hence it's blacker than black.
And is black hydrogen also? Black hydrogen also 40%? Or worse?
No, it's worse. It's worse still than just burning coal, because you're starting with pure carbon.
So gray hydrogen is pretty black, but not as black as black hydrogen.
That's right. Black. This is the trouble. We just don't have. It's like, the Inuit have apparently many different descriptive words for types of snow, and we in English lack them because snow is snow to us. We just don't have words for how black something can be if it's blacker than black. And that's a bit of a
black hydrogen,
problem.
Gray hydrogen. What is blue hydrogen?
So blue hydrogen is kind of like when you put those those pucks in your toilet or your urinal in order to make it look blue and sanitized. It's the notion that you can take, gray hydrogen and bury the CO2 and it suddenly becomes blue. So it's making hydrogen from natural gas and capturing and burying some of the CO2. That's what blue hydrogen is.
So it's gray hydrogen with an extra step.
Yeah, I call it bruise-colored hydrogen because it's kind of black and blue. Because okay. Of course, in order to do carbon capture and storage, first of all, somebody needs to pay you to do carbon capture and storage because it consumes energy and it requires capital equipment that somebody's got to pay for. And the energy that you use to run the carbon capture equipment is often made by burning fossils without carbon capture, so it results in a bunch of emissions. And then on top of it, you have the methane leakage up front, which first of all, you're taking methane in as a feed to make your hydrogen from, so part of that leaks. A world average 1.5%, but if you're getting it from Russia, it might be 7% of the methane that's leaking from the well to your plant. And then when you use that energy, which you get from burning natural gas, there's methane leakage associated with that. So, by the time you're done with that, there were a couple professors, Howarth and Jacobson, did a paper in 2022 called How Green is Blue Hydrogen? And they basically trashed the whole concept because they said, look, at realistic methane emission rates and using the 20-year time horizon for methane's global warming potential relative to CO2, this whole thing doesn't really even do anything. It generates as much CO2 as if you didn't bother. As much effective CO2 or global warming potential as if you didn't bother. Even though you're capturing some of the CO2 and burying it, you're not doing a good enough job of it. And as a consequence, the emissions are increasing per joule or staying the same or only very modestly, in the best case, very modestly reduced. So that requires you to do different hydrogen production a different way to get the capture to improve, and that becomes very expensive. And you also have to take methane that comes with very low leakage. So that means you can only get methane from certain parts of the world.
So much of your blacker than black label on hydrogen is from a climate standpoint. Let's for the moment set climate aside. Let's say that's not a constraint. Are any of these hydrogens viable from an economic and net energy standpoint in the future if emissions wasn't an issue or not so much?
So if CO2 emissions don't have a cost, or we're not worried about them for some reason or another, because I guess we've turned off our brains and ignored the science.
No, I agree. I'm just trying to parse out which of the impact. Yeah.
I'm just clarifying for you. If global warming weren't a thing, we would just keep making hydrogen the way we do now because that's the cheapest way. So the numbers are instructive here. In the United States, there's this wholesale price metric for natural gas called the Henry Hub price. It's kind of like the Brent barrel of crude or the West Texas Intermediate or whatever for natural gas. It's called the Henry Hub price. And they measure that per million BTUs. So $3.50 per million BTUs, which is about a gigajoule of energy, for those who want metric. $3.50 per million BTUs or per gigajoule is about what natural gas cost wholesale averaged over the last 10 years before the war and the pandemic. And you could turn $3.50 wholesale gas into $1.50 per kilogram wholesale hydrogen, not distributed to customers or anything, just at your plant gate, right? That's $11 a million BTUs or $11 a gigajoule. So we just multiplied the cost per joule by a factor of 3 by making hydrogen out of it. So would we want to burn any of that? No, we'd be stupid to burn any of it. It would be much smarter to just burn the gas, wouldn't it? So of course, in a future where decarbonization is not important, if we need hydrogen, we'll make hydrogen. If we don't, we'll just burn gas. because gas is cheap.
So the reason that we're making gray and blue hydrogen is for climate reasons, but we're not realizing the wide boundary impacts of the blacker than black hydrogen in its impact on the garbage machinery in the stratosphere, et cetera.
So we're making gray hydrogen. That's the way we make hydrogen now. Gray and black hydrogen is the way we make it now. And we emit all of that CO2 to the atmosphere. And hence, we only use that hydrogen for purposes as a chemical. Now, some of those purposes are environmental, like desulfurizing fossils before we burn them. But most of those purposes are just using hydrogen as a chemical. The only reason that you would ever do quote unquote blue hydrogen production, capturing the CO2, is if you got paid money for burying CO2. It's the only reason you would ever do it. So that only arises from the climate concern.
Got it. What other colors are there? Green.
Then there's green hydrogen. So green, of course, evokes all kinds of lovely feelings. And that's hydrogen that's made by deliberately electrolyzing water. So breaking water up into hydrogen and oxygen using electricity. And that electricity has to be itself green. It has to be renewable or nuclear or, depending on who you talk to. Some people want to call hydrogen made from nuclear electricity pink for some reason or another. But anyway, the notion here is that if you use electricity and the electricity has no greenhouse gas emissions associated with it, or very low greenhouse gas emissions associated with it, and you use that electricity to make hydrogen and oxygen from water, that hydrogen is now considered green. And of course, if you, to the extent that your electricity is green, the hydrogen is green. If you start using grid electricity that's got a bunch of fossils in it, it very rapidly can emit more CO2 than if you just made it from natural gas the normal way.
And in the large, glossy orders of magnitude scale of hydrogen in the future that's currently being promoted, especially in the EU, but also in the US, would that green hydrogen almost always have to be created in a plant or a factory that's near a body of water?
Okay, so are you asking about the water use concerns related to hydrogen, or
yep.
are you okay? Yeah, okay. So water use is really not an issue. It's the making hydrogen today using natural gas or coal takes a lot of water too. Making electricity using natural gas or coal takes a lot of electricity. And in fact, it takes orders of magnitude more water to make the electricity to make a kilogram of hydrogen than it takes to make a kilogram of hydrogen from water. Okay. So the way that you would, here's the way to think about it. Let's say that I have a project in Western Australia and it's a dry place. And I need water to make my hydrogen, but I've got lots of solar and wind electricity available to do it. To make a kilogram of hydrogen from 9 kilograms of water will take something between 50, very, very best case, and 65 kilowatt hours of electricity. Okay. To make the 9 kilograms of pure water from the ocean takes 0.035 kilowatt hours of electricity. So which of these two is a problem? In some sort of
desal plant?
Yeah. Desal plants, people are confused about water because, of course, water is essential to life and extremely valuable in that sense. And in another sense, is dirt cheap. I buy potable water up at the farm for $3.50 per ton. Okay.
So
per 1,000 kilograms,
So energy will be by far the limiting variable rather than water if we scale hydrogen.
If you need water and you have energy, the thing to do is don't make a kilogram of hydrogen. Use that energy instead to desalinate water and you'll get 14,000 liters of water in return. So the issue isn't water use, it's energy use.
Got it. Okay, that was super helpful. Now, I'd like to ask you some deeper questions on hydrogen and its potential. But before I do that, let me take a step back. Some of the articles and other interviews, and you even mentioned it earlier today, something you call the sins of thermodynamics. Can you briefly break that down and what these are and why they can create misleading ideas when people think about our energy future?
Yeah, I think this is a really important point because Václav Smil, as an example, is one of these guys who's just jumping up and down and trying to tell us that the transition away from fossils is going to, take forever and it'd be next to impossible to accomplish. And the reason that he draws that conclusion, I guess until fairly recently, he's kind of smartened up, but the reason that he draws that conclusion, or drew it in past, was that he looked at how many, joules of energy we use per person, or how many joules of energy we use on Earth every year. And what fraction of the number of joules of energy that we use comes from fossils, and finds out that most of it comes from fossils. And as a consequence, this is a terrible problem. What are we going to do? We have to replace, I don't know, let's pick a number, I don't know what the number is, but 10 units of energy we have to replace, and 9 of those come from fossils. Oh boy, we're in trouble. The problem is Dr. Smil's committing the second sin of thermodynamics, a sin against the second law of thermodynamics. And the second law of thermodynamics basically says that not all forms of energy are worth the same. The first law says that energy is conserved, so you can't make it or destroy it. You can only change its form from one form to another. The second law says that there are different kinds of energy that are worth different amounts, if you want. A good analogy is money. So we can have an amount of money denominated in dollars, right? But if I don't tell you whether they're Canadian dollars or Jamaican dollars or US dollars, I haven't really specified the problem, right? So if I've got a joule of electricity, a joule's worth of electricity, or a BTU or a kilowatt hour, you pick your unit of energy, that's not, if I tell you that it's electricity, that's telling you enough. But if I just say I have a joule or a kilowatt hour or a BTU of energy, that's not telling you enough. It's not telling you whether it's work, thermodynamic work, like mechanical energy or electricity, or it's heat, like chemical energy or heat, for that matter, a hot flowing liquid or steam or the like. So that's the people that commit the second sin of thermodynamics fail to realize that in the world of energy, we take these days an awful lot of chemical energy, which is a proxy for heat, right? So it's kind of the Jamaican dollars of energy, if you will. And then we put it through expensive equipment to convert it into work or mechanical energy in engines and power plants and the like. And that's kind of the American dollars of energy, if you will. And, if you just say, well, we need so many dollars, or we need so many joules or so many BTUs or so many kilowatt hours, and we fail to denominate whether they're work or heat or light or whatever, we're going to lead ourselves to wrong conclusions. And so, the reality of the situation is these days we burn fossils largely to make heat that we then use to make work, which we use to make things like electricity or to move vehicles. And in the future, we're not going to be starting with heat or chemical energy. We're going to be starting with work or electricity. So guess what? We don't need to convert all that electricity to chemicals or to fuels or to heat. We can use it to do work directly. The exchange rate's 1-to-1 rather than 1-to-3, which it is for heat to work, right? Or 3-to-1. You need 3 units of heat, more or less, to make a unit of work. So that's the second sin of thermodynamics, people messing up heat and work. And it leads to wrong conclusions. And in the future, our decarbonization journey is actually going to be about a half to a third as hard as these people imagine, because we'll be starting with electricity.
Okay. I understand that logic because I have long thought that energy properties are important: spatial distribution, intermittence, temporal, density, transportability, all these things are an American dollar is not equal to a Jamaican dollar.
Correct.
But
That's
that
right.
also
All of
works.
those things matter. Yeah.
But there is also it cuts both ways, right? Because right now only around 20% of the global energy use is electric, and we can change that a lot. And the more that we change it, the more we get that energy benefit that you're just talking about, because we don't have to do the 3-to-1 loss. But our current overextended global financial system and six-continent supply chain are dependent on this liquid fuel hemoglobin transporting goods around the world. And we can't change that overnight. So what are
Yep.
your thoughts on that?
Darn right. So here, well, first of all, we have to be really careful, right? Because whatever it was, 50,000 years ago or so, we started figuring out how to mess with fire. And ever since then, we've had this box on our heads, this intellectual firebox on our heads, which is need heat, must burn something,
Yeah.
right? And we got to get that box off our heads, and it's hard. In a world where you're burning stuff to make heat and then using that heat to make electricity, using electricity to make heat is dumb, right?
Right.
And in a world when you're starting with electricity, using electricity to just grind it up into heat is dumb, right? Now, there are times when it actually does make sense and is necessary, and we'll do it without any hesitation in the future. But there are applications where it's just not smart. So let's say I need comfort heat to keep my home warm because it's cold outside. You know, we're in Toronto here, and lots of snow on the ground at the moment. And I've got electricity. You know, bunging it into a resistor, you know, a baseboard heater or whatever to make heat would be kind of nuts, right? Now, people do it, but it's not the best idea. The thing to do instead is to use run a machine with that electricity called a heat pump, and then pump heat from outside into the home, and hence get 3 joules inside the house for every joule worth of electricity we use. So there's the difference.
So why don't we do that? Where I live here in northern Wisconsin, by the way, if it starts to get cold, my initial reaction is not to turn up the thermostat, but put on a sweater and a pullover and stuff. That's my initial reaction. But there are, where we have in the office here where I'm doing this podcast, there is electric baseboard heat. Why has culture gone that direction instead of heat pumps? And could we have a mass adoption of heat pumps? A little bit tangential, but not really.
Sure. No, this is really important. And the answer to that is it depends where. So, you know, Wisconsin, Minnesota, Alberta, Saskatchewan, those are places that, you know, it gets quite cold in the winter, much colder than it gets here in Toronto, as an example. So heat pumps become harder, and part of the year you end up having to basically grind up electricity to make heat the old-fashioned way. So if your alternative is to burn a fuel and to dump the CO2 to the atmosphere, that's going to be super cheap in comparison. And that's the reality in Toronto right now. I mean, I ran the numbers for my house, and of course, being who I am, I wrote an article about it where I warned everybody at the beginning, warning, this is all about numbers. And if you don't like numbers, just stop reading before I hurt you. But I ran all the numbers for my house, and I looked at what electricity cost me, you know, everything in taxes, debt retirement charge, all of that crazy stuff. And I worked out, you know, we bought so many kilowatt hours last year, and we paid so many dollars to Toronto Hydro, and it cost us this much per average kilowatt hour. And then I looked at, we burnt so many cubic meters of natural gas last year to heat our house, to heat our water, and to cook our food. That cost us so many dollars. So that's so many dollars per equivalent unit of energy, you know, per kilowatt hour. And I compared the two, and I went, okay, fantastic. If I were to switch over to baseboard heaters from my natural gas boiler that hydronically heats my house in a very efficient way, but emits a lot of CO2 to the atmosphere, I would drop my CO2 emissions by quite a lot, because the grid here in Ontario is mostly nuclear and hydro, and as much wind as natural gas, which is about 7% of each, and no coal since 2013. So I dropped my CO2 emissions by a lot. Okay. But the cost per ton of CO2 emission that I averted would be very high, like hundreds and hundreds of dollars per ton. It would be way smarter for me to buy an electric car, which, by the way, I did. Okay. But I also built one, converted one, a gasoline engine car to an electric car in 2014, just to figure out what was going on and make sure that the stuff was actually what it was cracked up to be. Certainly here in Ontario, the lowest hanging fruit of decarbonization is not home heating, buying a heat pump, it's transport, because transport right now uses 100% fossil fuel, or 90% fossil fuel and 10% bioethanol. And, you can get the benefit of the higher efficiency of the electric drivetrain charged directly with electricity. And by so doing, that car that I converted, same car, identical car, just different drivetrain, I dropped its operational CO2 emissions by 97%. And relative to my Prius, which is the most efficient car you could buy in Ontario without a plug attached to it, I dropped my emissions from my commute by 94%. Okay. So you see the efficiency gain that you get from no longer converting, chemical energy into work by using electricity directly. That's a tremendous benefit. And of course, with heat pumps, the real benefit is in places where it doesn't get that cold in the winter, like Toronto, as an example. I mean, we get to minus 25 degrees Celsius only a few days a year. And up to minus 22 degrees Celsius, a heat pump will give you 2.2 joules of heat for every joule of electricity you put into it, which is pretty awesome. So, but the problem is, even if I were to buy a heat pump and I take that coefficient of performance, that multiplier on how much heat I get in per how much electricity I put in, it's still going to cost me quite a few $100 per ton of CO2 averted. So I'm not reaching out to change my gas furnace into a heat pump anytime soon, even though in Canada we're going to have a $170 a ton carbon tax in 2030. Gas is just so cheap, and retail electricity isn't cheap here. And as a consequence, it's just not, the economics are not particularly good. I might change because I want to make the world better. But as an economic actor, as somebody making decisions about what is best for my pocketbook, that's not the best way to spend my money. Buying an electric car certainly was.
And there's probably many aspects of this conversation that would give you different decisions if you're trying to be a good citizen of the planet versus a consumer. So I would love to talk to you about
burning hydrogen to heat your house is nuts. Like, that's just not good economics.
Are there people that do that?
Well, they're talking about it in the UK in a big way. There are, in fact, I'm co-founder of an organization called the Hydrogen Science Coalition, which is a bunch of financially disinterested engineers and scientists and academics who know a lot about hydrogen and its applications, but don't have any money tied up in it one way or another. Like, I don't make my living from hydrogen. I don't make my living from batteries or alternatives to hydrogen. I make my living as a technology consultant, and that's what I do. So I can say whatever I like, and if customers don't like it, they can just go find somebody else, and that doesn't bother me. At the point being here that a big thing that the Hydrogen Science Coalition has been doing is trying to help out these residents of a couple communities in the north of England, the town of Whitby and the town of Redcar in particular, who the local gas utility wants to do a hydrogen heating trial on their homes and wants to compel their compliance. It's not like you sign up for this and they'll pipe hydrogen into your house if you want it. No, they want to convert all the gas mains over to pure hydrogen and rip out all your appliances in your home and replace them with hydrogen appliances. And they're doing this.
I mean, the initial response that an intelligent person would have to that statement is, well, those people have to be smart people, and so there's something that you're missing. What is their angle? Why do they want to do that?
Well, they're a gas utility. In a decarbonized future, unless they can sell something else in their pipes, they're out of business. So yeah, they're smart people. They understand that their days are numbered. They have to sell hydrogen. It's existentially important to them. And by the way, the kind of hydrogen they want to sell is blue, made from fossils with carbon capture, not green. Green hydrogen is just being used as the bait. Because if you've got electricity And your choices are make it into hydrogen and then put it in the piping system and burn it in your house, or instead feed it to a heat pump. The difference in electricity use between those two chains is a factor of 5 to 6 in favor of using the heat pump. So if you've got to pay for electricity and electricity is not cheap, I guarantee you're going to want to buy the device that uses 1/5 to 1/6 as much, rather than just using the gas pipes and having to buy a new boiler anyway, because the old boiler can't run on hydrogen anyway.
So the economic and the climate decision for those communities in England would be heat pumps instead of new infrastructure to burn hydrogen in their homes.
Absolutely, because the mean winter temperature in the UK isn't cold enough to ever need to use something other than a heat pump.
Right.
It doesn't get to minus 40 in the UK.
Right. Not until the AMOC totally shuts down. That was a joke.
Yeah, then maybe it will. That's right, because they're north of us by a long way.
Okay, so let's get to the heart of this conversation on hydrogen. On your work on this topic, perhaps you can start off listing, maybe in the order of importance, what the biggest problems are with scaling hydrogen the way that we're being told right now. You've mentioned a couple things, either from an implementation or a risk perspective. Do you have the 5 bullet points or an elevator pitch on that?
Yeah, it's super easy. So our focus needs to be on fixing the problem of hydrogen. So there are no regret uses for hydrogen that are plentiful. Making ammonia to make fertilizers is one of them. Making other chemicals is another. The direct reduction of iron ore to iron metal is another. It's going to be a big boom in the future. And right now, we're doing it with syngas mixtures that contain fossil carbon, and we've got to switch to pure hydrogen for that. Those are all no regret. We should be focusing on those, right? I keep hearing people talking about the so-called hard to decarbonize sectors. Oh, well, we've got to have hydrogen for the hard to decarbonize sectors. And it's like, great. If there are hard to decarbonize sectors, there must be easy ones. Why aren't we focusing on the easy to decarbonize sectors, which are transport, as an example? We should really be focusing on the easy to decarbonize sectors, but we should be decarbonizing hydrogen for use as hydrogen first. And let's say we get to 70% of the world's hydrogen being made from renewable or nuclear electricity. If we get to that point, then maybe at that point, decades from now, we can start thinking about wasting hydrogen on inefficient uses like as a fuel. So it's literally that simple. It's all about the use cases. There are use cases that make sense. Those are hydrogen being used as a molecule or as a reducing agent to replace fossil reducing agents. And then there are use cases where hydrogen is being used as a fuel or an energy storage medium or an energy transport medium. And all of those are questionable when you dig into the details. And, okay, here we are in a very short conversation. I don't have the time, the hours to explain in detail why that is. I refer people to my writings, which you can find on LinkedIn or on my blog, on my website.
We'll put them in the show notes.
Yeah. So, you can refer to those articles, and I explain in detail why it is that hydrogen and hydrogen-derived molecules are not the new LNG, because nothing is the new LNG. And why it doesn't make sense to use hydrogen for transport, because the lion's share of transport applications can be electrified either directly or via batteries, and the ones that can't be are a poor fit for hydrogen, because hydrogen is just too bulky. It's too big, too low in energy density per unit volume, and too difficult to distribute, and hence expensive to distribute as a fuel. So people want to make it into other things.
How is the energy density of hydrogen compared to methane or gasoline?
So hydrogen as a liquid is about a quarter the energy density of methane as a liquid, so LNG. And hydrogen as a gas is about a third the volumetric energy density of methane as a gas. So you have to move three times as much volume.
Everything else being equal, if we scaled hydrogen as a fuel globally, the devices that we used it in would have to have much bigger tanks, everything else being equal.
That's one way to put it. So let's say that we were to try to make liquid hydrogen at 24 degrees above absolute zero, using 30% of the energy in the hydrogen to just make a liquid out of it, and then transport that. We would need 4 times as many ships of the same size to carry the same amount of energy as we do today. But the real issue is how much energy is being wasted in that process. I mean, it's buy 10 kilowatt hours, get 1 or 2 back at destination. It's just, great business if you're selling electricity, terrible business if you're a consumer of electricity. So not all that smart. And then when you look at trying to stuff hydrogen into the natural gas network as a replacement for natural gas, you run into all kinds of problems. You run into problems with the materials of construction being wrong. You run into problems with compression. It takes 3 times as much energy to compress hydrogen, like a unit of energy in the form of hydrogen, as it does to compress a unit of energy in the form of methane. So it's much lossier to move through a pipeline.
What
so there's
does
all kinds of
lossier
problems
mean
like that.
again?
It just
I've
means
heard.
that you lose more of the energy in the process of doing the thing, right? So if you look at natural gas, moving it from place to place is fairly efficient. If you replace natural gas with hydrogen, if you want to move a joule of hydrogen from point A to point B, it's going to take 3 times as much energy as if you moved a joule of methane from point A to point B.
So let me ask you this, Paul. Instead of saying what you think should happen, just put on your speculative hat, and given the tea leaves of what's happening in Europe, in the UK you mentioned, and the narratives with subsidies for hydrogen seems to be picking up momentum. What do you think is going to happen with hydrogen?
I think tens of billions of dollars are going to be spent trying to use hydrogen for inappropriate purposes. I think an awful lot of people will earn an awful lot of salary on the attempt, whether it succeeds or fails, and it will fail. And I think that we will end up decarbonizing the economy by electrification and not by virtue of fuel substitution. I think, honestly, hydrogen's role in heating and transport are both niche at best. They're very small, minor, secondary applications in heating and transport. Maybe we'll use some hydrogen to boost the yields of biofuels production for things like transoceanic ships and aviation, but we'll use biofuels and not hydrogen for those purposes because they're a much better fit. And I don't think that we're going to have a hydrogen economy. I think the whole hydrogen economy thing is based on the notion of hydrogen as a fuel, and that's a notion that doesn't hold weight as either or it doesn't hold water as either a decarbonization strategy or an economic proposition. I think that means a lot of misery for a lot of people living in countries like Japan and South Korea, as an example, that are totally dependent on imported energy, are not good friends with their nearest land neighbors, and have a lot of heavy industry and are very hungry for energy per capita. I think those guys in a decarbonized future are in big, big trouble. And I think they hope hydrogen will save them, but hydrogen won't save them, honestly. It's a false hope.
I emailed you a few days ago about a big article that was been floating around in Science Mag, and this weekend there was an article in the New York Times talking about the new discovery of enormous amounts of low-carbon hydrogen deposits under Earth's surface. So does this promise here, does this story fall victim to the sins of thermodynamics? Is this a big deal or a bunch of hand-waving?
Well, to my knowledge, there's one producing well in the world. It's in Mali. They were drilling a hole for, drilling a well for water and ended up producing hydrogen at fairly high purity. I think the likelihood that that's widespread on the Earth, that we've just been drilling holes for water and oil and gas in all the wrong places and magically avoiding it, is pretty low. I think there's kind of a gold rush mentality. There's certain geological conditions when hydrogen might be produced. I think they're pretty rare. I hope we find a bunch of, geological hydrogen that's not full of CO2 and methane that we can actually use. But I'm not hopeful that that will be a major source of hydrogen anytime in the future. I think it's mostly a gold rush.
Time has been flying here. I want to be respectful of your time. If you don't mind, I have some questions that I ask all my guests near the end of an interview. So, given your lifetime of work on energy sustainability issues and your awareness of the difficult times we're in, do you have any just personal advice you give to people or to listeners of this show on how to navigate these times?
Yeah, it's tough. It's very easy for me to say, as somebody that's quite senior in my career. I've gone out on my own as a consultant and having the time of my life doing it, honestly. Uh, but what I do is, and what I've tried to do my whole career, even when it was hard, was I tried to ask myself, is this work making the world better? And if it's not, don't do it. I realize people have to keep body and soul together, and you got to earn a living. And if Shell comes knocking on your door and nobody else is knocking on your door, I guess maybe you end up working for Shell. Now, I never did. I never made that choice, and I think I feel better about it for not doing that. But I mean, those guys were customers. Those guys were customers of mine. Let's be clear. I made lots of money from the fossil fuel industry, and what we were doing was trying to make the world better in that context. So we were always trying to, reduce energy use, reduce waste generation, make the processes more efficient, reduce how much capital was required, make sure the equipment lasted longer, whatever. We were doing something to make it better. So that's my advice to people is, regardless, even if you're working in the fossil fuel industry, try to do that work in a way that makes the world better. And if you can't, find something else to do for a living. That's it. Real simple.
I resonate with that, and I wish we had the sort of economy where there were choices that people could do the better things for the future, and maybe that'll change at some point.
Yeah. And I would say that I something I found very frustrating in my career is I was helping people develop new technology, and I'd have smart, creative, motivated people come in all the time, and they'd say, "Hey, we've got this great idea. We're going to decarbonize X, whatever X is, and if we get $50 a ton carbon tax, we'll break even." And so we'd design them a pilot plant, and they'd run it for a couple of years, and they'd say, "Yeah, well, we were optimistic. We actually need $100 a ton now that we know everything." And they would bet that the world would pay them $100 a ton, and then the world wouldn't do it, and they'd go broke. And you only have to do that a few times before you go, is this a technical problem or is this an economic problem? So without the economic problem being solved, a lot of us technical people are basically twiddling our thumbs. We can't fix it.
Yeah, I hear you there. What specific recommendations do you have for young humans who become aware of our economic and climate and broader systemic issues?
I would say don't panic. The great advice that's on the cover of the Hitchhiker's Guide to the Galaxy. Don't panic, because panic doesn't help. Don't fall prey to hopium, which is the willing suspension of rational thought. Don't let your hope overwhelm you. But if you got a choice between hope and despair, and those are the alternatives, pick hope. And technology can do a lot of good in the world if it's directed properly. Don't blame technology. Don't become a Luddite. Don't think that there's some, agrarian past that we can return to when everybody was in harmony with nature. Be practical and focus on solving real problems every day.
What do you care most about in the world, Paul?
Yeah. What do I care most about in the world? It's a values question. I love my family and I love the intellectual challenges of my work. I love being creative and doing interesting things and all of those things. I guess if what you're really asking is what do I value the most, or what would I fix about the world to make it a better place, it would be that right now we don't value the way we exploit the world, and we don't, as a as people living in a society that has the rule of law and has government, we don't hold governments to doing what they need to do for collective benefit, which is tax and regulate for collective benefit. We've been conned into this notion that taxation is theft and regulation is just red tape and governments are worthless. And that's a con. Like, that's a straight up con. So I would say it's something that we need to get our heads around and stop believing, because it's leading to just further destruction of the earth that we live on. And, if I love my kids, I want them to have a place to live in. That's not a torture chamber, because past generations have made dumb decisions.
So you would be an advocate for a carbon tax over time?
Oh, I've been an advocate for carbon taxes for 30 years. And here's the thing. A lot of people don't realize that in Canada, we were told we would never have a carbon tax. We were told that. We were told that repeatedly, loudly, shrilly. We have a carbon tax in Canada. It's been defended in 2 federal elections and in a Supreme Court challenge. It was challenged at the Supreme Court by 4 provincial premiers who are closeted climate change denialists and couldn't bear the thought of carbon tax. And the Supreme Court upheld it. And it's the law of the land, and it's increasing to $170 a ton by it's increasing to $170 per ton by 2030. And it's widely supported by the population. And the reason that it's supported by the population is not only do the population in Canada kind of get it, they understand that climate change is a real thing and we've got to do something about it, but we also get the money back. So it's not like it's going into some nebulous government coffer and then just being spent on, schools and hospitals and whatever the priority is of the day. We get the money back at the average rate. Makes a huge difference, right? So poor people who don't consume much and hence don't emit much because they don't consume much, they get more money back than they pay in tax. Their lives get better. They get rewarded for their low emissions lifestyle. And rich people who emit a lot because they have a lot and they consume a lot, they have all the capital in the world to invest in reducing their emissions if they choose to do so. Because they don't like paying this carbon tax. So it's a very well supported thing, and I absolutely support it. I think it's fantastic and necessary, but insufficient. Like, that's not enough. You got to do that, but you got to do more.
I didn't know that about Canada. So what in your own work, Paul, are you most excited about on your contribution to our collective future? What are you working on now that's exciting and hopeful and gets you going?
So I give my clients, I put 4 tests on my clients before I do business with them. First of all, that very most important one is, are they making the world better or are they making it worse? I make a subjective value-based decision on that basis, and I determine whether I'm going to work with them or not. I have to be able to help them, right? So I have to be able to contribute something that will make it worth me being part of it. Otherwise, I'm just grinding my gears and not really helping. They have to be able to pay me, right? Because I do enough pro bono work through the Hydrogen Science Coalition and other things, and I need to make a living just like anybody else. And the 4th one that's really undervalued by a lot of people, but really highly valued by me, especially as a private consultant, is I got to have the impression that it's going to be fun. That these are going to be people that are going to be a good time to work with, that they're not going to be officious and difficult and making my life miserable, that they're going to be cool and they're going to be fun. So I give people those 4 tests before I work with them. And I'll tell you, that makes for a very satisfactory working experience. As far as what kind of projects am I working on that are making the world better? Well, a lot of that I can't really talk about because I'm under non-disclosure agreements with people that are developing new technology. But I can tell you I'm working with groups of people that are doing things like novel ideas for energy storage, both as electricity and as heat. People that are working on materials of construction that are lightweight and hence will be a better choice for mobility applications, as an example. People that are improving materials of construction in terms of their impact on the environment. working on people that are working with people that are trying to make hydroelectricity in tropical climates greener. There are methane and CO2 emissions associated with hydropower in tropical environments that are not negligible and need to be dealt with. And these guys are doing clever things working on that. I'm working with all kinds of people on all sorts of things, but working on battery materials and working on electrifying heating and electric vehicle applications and all sorts of cool things. I'm having a riot.
You wake up in the day and you almost don't need coffee. Sounds like you were quite motivated and engaged.
Oh yeah, no, I'm having a good time, and that's certainly something that was a pleasant surprise to me, because I'd kind of retired and hoped that I would pick up enough consulting to keep myself occupied, keep my brain in the game, and maybe make some money to travel and do a few things that I wanted to do. And I'm actually working almost a little bit too much. So.
Thank you so much, Paul. And if I do come to Toronto in April, I'll email you. Maybe we could go grab a coffee or a beer or something.
Absolutely.
If you enjoyed or learned from this episode of The Great Simplification, please subscribe to us on your favorite podcast platform and visit thegreatsimplification.com for more information on future releases.